Welcome to this explainer. For decades, we've all stared up at the red planet with this sci-fi dream of going there. But today, we're shifting our focus. We're looking at the harsh, practical reality of actually surviving its brutal environment once we arrive. We're going to dig into the hard data and the literal engineering constraints standing between us and a permanent human settlement. Let's kick things off with a pretty staggering number, 12 out of 19. That's the historical success rate for robotic Mars landings. Think about that for a second. Mars is essentially a graveyard for over a third of the robots we've hurled at it. It instantly tells us that everything we're discussing today is quite literally a matter of life and death. I mean, if the odds are that tough for autonomous machines, just imagine the immense pressure when actual human lives are aboard. So, to beat those odds and establish a permanent foothold, this explainer is going to act as your chronological survival guide. We'll be covering 1. The ultimate survival challenge. 2. Surviving the landing. 3. Powering the Martian base. And 4. Extracting local water. All right, let's jump right into part 1, the ultimate survival challenge. We really need to wrap our heads around the fact that Mars is a world actively trying to kill us. Seriously, we're dealing with an incredibly thin atmosphere that gives practically zero protection, global dust storms that can block out the sun for months, and this corrosive, freezing soil. And what's really fascinating, well, actually kind of terrifying, is that our trusty Earth-based engineering solutions, they just won't save us here. We can't just copy and paste our tech. Down here on Earth, we rely on a thick atmosphere to brake our spacecraft. We've got abundant sunlight for solar power and liquid water right on the surface. But on Mars, every single one of those comfortable assumptions is violently stripped away. Moving on to Section 2, Surviving the Landing. Because obviously, before we can build a base, we actually have to touch down in one piece. And that brings us to the very first massive hurdle: entry, descent, and landing. Engineers call this EDL, and it's widely considered one of the absolute highest risk phases of spaceflight. Astronauts are going to face a terrifying multi-stage sequence. First up is atmospheric entry, where the spacecraft literally has to survive immense hypersonic thermal loads and aerodynamic forces. Then comes the transition to supersonic descent. Now, traditional parachutes are deployed here, but they suffer from extreme wind drift in the Martian atmosphere, which can blow landers kilometers off course. Finally, the vehicle has to ditch the parachute altogether and pull off a powered retropropulsive touchdown to softly land on the rocky terrain. This whole sequence brilliantly illustrates just how much hyper-precise engineering goes into this phase. Historically, landing error zones on Mars were huge, spanning hundreds of kilometers. But today, through active guidance, terrain-relative navigation, and some incredibly sophisticated propulsive systems, we're shrinking that landing error zone down to pinpoint accuracy. For human landing systems, we are aiming for an error zone of less than 1/10 of a kilometer. Now, the really crucial point during that final powered touchdown is managing what engineers call plume surface interaction, or PSI. See, because those retropropulsion engines fire directly against the ground to slow the vehicle down, they kick up an enormous amount of high-velocity debris. It basically acts like a giant high-velocity sandblaster, causing severe surface erosion right underneath the lander. And worse, all that ejected rock and dust poses a critical risk to the vehicle itself, not to mention any nearby surface habitats or supplies we might have already parked on the ground. So, let's say we've perfectly navigated the entry, we've managed the debris, and we've safely arrived. Awesome. The crew is on the surface. But just a minimal 30-day mission for 2 crew members living in a pressurized rover requires at least 10 kilowatts of continuous power. And that brings us right to our next major hurdle. Section 3, Powering the Martian base. Here we face a massive energy trade-off. We have to pick a power generation system capable of surviving a vastly different solar and atmospheric environment than Earth, because without reliable power, life support fails, communication goes dark, and making rocket fuel stops entirely. Now, solar panels might seem like the no-brainer choice, right? After all, they power the International Space Station and all our satellites. But deploying them on the red planet introduces some massive vulnerabilities. The Martian surface is absolutely not a friendly place for delicate solar arrays. They'd have to fight through a severely reduced solar flux. At its absolute best, Mars gets only 45% of the solar energy Earth gets. On top of that, you've got a 25-hour day-night cycle, which means any solar base would need massive, heavy batteries just to survive those long freezing nights. And then there's the dust. Mars is infamous for these crazy regional and global dust storms that can last for weeks or even months, almost completely blocking out the sun. Plus, even when the sky is clear, fine dust just constantly settles on the panels and ruins their performance. This exact dust accumulation is literally what killed the Opportunity rover. So, when we compare solar power and its heavy battery storage against high energy density nuclear fission, a pretty stark reality emerges. If we rely on solar, we're going to have to invent complex robotic wipers, tilt mechanisms, or electrodynamic dust removal systems just to keep the panels clear. But the bigger realization is that for human survival, we absolutely need a power source that doesn't care if it's pitch black outside or if a global dust storm is raging for a month straight. Because of this absolute need to mitigate the risk of mission loss, NASA has officially made their call. Robust, scalable, nuclear fission is the baseline primary power generation technology for early crewed Mars architectures. It just offers way too many advantages when it comes to reliability and resilience compared to anything else. These fission systems are amazing because they package perfectly into tight, volume-constrained spacecraft. They're completely unaffected by the day-night cycle, totally ignore atmospheric dust, and they can reliably churn out that essential round-the-clock power. We're talking energy for everything from life support systems to the incredibly energy-intensive process of manufacturing ascent propellant for the trip back home. Okay, great, the base is powered, the lights are on. But to truly establish a permanent settlement, and critically, to create that rocket fuel for the astronauts' return journey, we have to learn to live off the land. We absolutely cannot just ship all our water from Earth. The expense would be astronomical. And that brings us to our final, absolute necessity. Section 4. Extracting local water. Now, finding water on Mars isn't actually the problem anymore. We know it's there. The real challenge is extracting it, using machinery that won't totally degrade in that corrosive, freezing dirt. We need systems that function in an environment far harsher than anything we see back home. Recent research from Dr. Vasilis Ingilzakis at the University of Strathclyde breaks down our practical options into 3 potential sources: drilling down into buried subsurface ice, baking the moisture right out of the Martian soil, or attempting to suck water vapor directly from the incredibly thin atmosphere. Let's dive into this breakdown and see how these actually stack up. Melting subsurface ice gives us by far the best energy-to-yield ratio. Once your drill gets through the rock to the ice deposits, the energy it takes to melt that ice is incredibly low compared to the massive amounts of water you get back. It's highly viable as our primary supply. On the flip side, trying to get soil moisture by heating up the dirt, that requires huge amounts of energy for a very tiny water yield, so that's strictly an emergency backup. And atmospheric harvesting, it's intriguing for remote areas that are far from ice deposits, but the air is so dry you'd have to run the machinery nonstop just to scrape together a usable amount. But, there's a fascinating catch to all of this. As we design these extraction technologies, we must also strictly adhere to planetary protection constraints. Essentially, we have to make sure we aren't the alien invaders. We have to ensure our drills and heaters don't introduce Earth microbes into the very resources we're trying to study for signs of past life, while simultaneously using those same resources to keep our astronauts alive. It's just a massive engineering tightrope. Ultimately, all of this incredible engineering, from shrinking our landing ellipses down to pinpoint accuracy, to deploying nuclear reactors in dust storms, to inventing completely clean ice drills, it all serves this one fundamental goal beautifully stated in the research: making Mars a practical asset. We are moving away from the era of simply discovering resources and entering the era of actually utilizing them to sustain human life. So, what does this all mean for us? We've seen today just how brutally unforgiving Mars is. It actively fights human presence at literally every stage, from the fiery descent through the atmosphere down to the freezing, dusty surface. It leaves us to wonder, as we look toward the Artemis missions on the Moon as our ultimate testing ground, what other incredible engineering miracles are we going to need to invent before we can finally, permanently call the red planet home? Thanks for exploring this explainer with me, and keep questioning what it takes to push the boundaries of human survival.